It is, in fact, there's a bit of yellow cable in the shot. What's that all about? No, should we leave it there? Let's just leave it there as a bit of a tease. Okay, what we're looking at then today, Steve?
Well, the clue's over there. But no, I thought as we're recording this, it's a few days after the 50th anniversary of Ethernet. Ethernet's, well, it's become the network to rule them all, even though it's not a ring network. Well, Ethernet was created at Xerox PARC, like lots of things, by Bob Metcalfe and others back in 1973. At that time, there were lots of different network technologies being developed. We've talked in another video about Aloha, which was the wireless network being created in Hawaii to connect their computers up to terminals and other machines dotted around the islands. But at PARC, they were interested in creating a local area network, a network for connecting computers within a single area, perhaps within, I think the paper suggests around 1 kilometre would be the maximum length. And when you actually think about that in terms of distance, you think, well, 1 kilometre's quite a big distance.
So for our American friends, that's just over half a mile, right?
It's 5/8 of a mile. But actually, when you think about how computers get connected up, you can very quickly get, even within a single room, 40 or 50 metres of cable. In this room, we've got about 40 computers dotted around the place. There's our cyber security lab, a cyber physical lab as well. But we can use it as a proxy to think about how much cable we'd actually need. Let's take these two computers here. We'll use the monitors as a proxy rather than actually trying to find the actual devices underneath the desks, because they're very small these days. They're about 1 metre apart from centre to centre. That's roughly 1 metre, 3 feet for you people who deal with weird inches and feet. So we need 1 metre of cable to connect these two up, roughly. Over here, another metre, that's 2 metres to connect 3, 4 metres, 3 metres, 4 metres, 5 metres to get here, give or take, 6, 7, 8, 9. We need 9 metres just to connect the 10 machines on this desk. And we're going to continue the cable because they were trying to do it with a single cable, and we'll see why in a second. So we need to continue it. Here, this is probably another 3 or 4 metres, 13 metres, and then 14, 15, 16, 17, 18, 19, 20, 21, 22. So we need 22 metres to connect the computers over on this side of the room. There's the same over in that side of the room. So that's another 22 metres of cable, that's 44 metres. And then what, let's say that's 5 metres. So we need about 50 metres of cable. I mean, that's assuming we can put them 1 metre apart. When you were dealing with some of the original Ethernets, there was rules that say you actually have to have them 2 metres, 2.5 metres apart. So actually, when you're thinking about the cable snaking around the whole room or a whole building, 1 kilometre isn't actually that long. If we go to a diagram, we need to think about how we can connect computers up. If we've got 2 computers, then connecting it up is quite straightforward. We can put a cable between the two. This machine, let's call this A, can talk to machine B. Let's add a third machine, machine C. I'm getting imaginative, C for computer. Now let's say we want to connect C up to the other 2 machines as well. Now we could add another cable, let's connect C to B. Now B can talk to A and B can talk to C, but A can't talk to C directly. It could send a message to B and B could then pass it on, but it can't talk directly. If we wanted it to talk directly, then we'd have to add another cable in. So we now need 3 cables, 3 machines. Let's add in a 4th machine, and I'm sure you can guess what this one's going to be. Yep, that's right, it is D. I should have gone for E, just to sort of...
Number 4.
Yeah, number 4, just to really trigger some people. We can do the same thing again. We can connect this up. Now it can talk to machine A, but it can't talk to any others directly. We can connect it up to machine C, and then connect it to machine B, and we now need 1, 2, 3, 4, 5, 6 cables to connect 4 machines. And as you add more machines, if you want everything to be able to talk to everything else directly, then the number of cables goes up. If you had another one, you would need another 4 cables adding. So you've got 10 for 5 machines. If you want another one, you've got 15 for 6 machines, and so on. You get an explosion of cables, which would also come with an explosion of sockets on the back of the machine, and by the end of it, your machine will be huge because you've just got sockets on it to connect to every other machine. And then as soon as you want to actually plug another machine in, you've got to add another socket. And for some applications, having a mesh like that, a fully connected mesh like that, is really useful. So what most networks do is, rather than directly connect everything, they share a medium, they share some access medium that they can then speak over. And so the idea in Ethernet was that rather than having each machine directly connected to each other, as so, what they would do is they'd have a single cable, and you need to terminate it at each end, and then you would connect each machine to that cable. So we had machine A, and that's connected to the cable, machine B, and then we have machine C and machine D. And we can connect that to the cable as well. We now have every machine connected to every other machine, and machine A can send a message over that cable to machine C, no problem. Machine C can send a message over it to machine B can send one to machine A or to machine D. The problem now is how do we make sure that two machines aren't transmitting at the same time? How do we make sure that when machine A is transmitting, that machine B and machine C don't try and transmit at the same time? Because if they do, it'd be like two people speaking at the same time. You'd end up with a confusing...
Yeah, and then nobody would
really able to understand what's happening because both Sean and I are talking at the same time and no one can hear what's actually being said. So we have to do what's called media access control. How do we make sure that A can transmit and then it can be received by everyone? The advantage of this is that if you wanted to add another machine onto the network, let's add machine E over here, then it's dead easy. We can just sort of take the cable to that machine, add it in, and it can talk to everything over the same shared medium. The beauty of what came in the original Ethernet specification that was proposed in 1973 in the Xerox memo that's wonderfully Xerox sensitive. I think this was released at Ethernet at 30, at least that's what it says on the back of the PDF that we've got here. So this memo describes how they were thinking about how they would solve the media access control problem. How do you make sure that only one machine is transmitting at the same time? I made a joke at the beginning about this bit not being a ring network. Ethernet, as it's laid out here, is a bus network. We have one long piece of wire, which is commonly referred to as a bus in computer science hardware terms, and everything is connected to that. Interestingly, there's a wonderful bit in the memo about why it's called Ether and not CableNet, or amusingly the Alto Aloha network, because they did borrow quite a few ideas from Aloha, which had come out a couple of years earlier. Bob had the foresight to say that while we may end up using coaxial cable to carry our broadcast transmissions, it seems wise to talk of an ether, going back to the idea of the ether, which electromagnetic signals travelled through back in the sort of late 19th century ideas about how things worked. Of course, now we know it doesn't quite work along those ideas, but the name stuck. It seems wise to talk in terms of an ether rather than the cable for as long as possible. This will keep things general, and who knows what other media will prove better than cable for a broadcast network. Maybe radio or telephone circuits. Radio, wireless, Wi-Fi. Modern Wi-Fi is based in part on Ethernet. Power wiring. We have power-based Ethernet things, frequency multiplex cable TV, cable modems for transmitting things, microwaves or any combination of that. It really is quite insightful about where 50 years of networking is going to go. And there's a wonderful diagram of Wi-Fi predicted in the 1970s. But of course, you already had Aloha running over in Hawaii, so perhaps it isn't that surprising. So their idea would be that you'd create your network with a single piece of cable. This isn't the sort of Xerox PARC Ethernet that we've got here. This is the sort of what came a bit later on after it had been standardized and sort of adopted by everyone in the early 80s. This is what's called 10 base 5. And so you'd have a huge cable, and the idea would be that you would have this running around the building, running in the ceiling, and the specification, I think, meant that you would only be able to put computers every 2.5 meters apart from it. So you'd have that, and then you'd have devices like this, which would physically puncture the cable. And if I just take it to bits, we can sort of see what's going on. So we've got the circuit board here. This is the transceiver that actually talks to it, and it connects to the computer there. We'll come to that in a second. But if we lift that off for now, we can see that there are 3 spikes, and they're quite sharp, sitting there. And these go through, and on the other side, they puncture the actual cable. 2 of them are going into the screening on the coaxial cable, and then one goes all the way through to the actual signal wire in the middle. And so that enables it to make a connection without having to break the cable, which gives you good signal integrity and just makes things, I won't say easier to do, because putting these things on was probably a nightmare, but compared to having to sort of splice the cable, put connectors on. It was relatively straightforward. Of course, later you had 10^2, which did do that, use T-pieces and connect things together. So you'd have your connection to the Ethernet, to the cable there, and then you'd have your transceiver sitting on top of it, which of course is now connected through to that cable by the connections here. Interestingly, this design, this is a digital one, you can put the circuit board on either way, depending on whether you want the cable to come out the left or the right. This part of the circuit board would take the data from the computer and modulate it into the format that was transmitted over the actual cable. And it also did a few other things, as we'll come to and look at in a second. So this is the actual bit. That would then sit on top of it like that. And then you would have a cable. So this would be in your ceiling void or under the floor perhaps. You wouldn't have this sort of running behind the computer. I mean, these are actually referred to colloquially as vampire taps because obviously you've got sort of pins piercing into the Ethernet cable to suck the data out. A bit like Dracula piercing your neck to suck the blood out, I guess is the sort of idea behind that. What you then have is a drop cable, like so, which would connect onto there. So this is a 15-pin cable and it's got locking connectors on it. So once you've connected it, you can't get it off. And that's got the transmit and receive from the data that's on here back over a couple of twisted pairs. And it's got collision detection, we'll come to that in a second, and power for this device. These were designed so that if the power went off, they would just not be there, effectively electrically equivalent. And then you would connect this back to the back of your computer, and you'd have your network card, and then you would plug that in like so. And so your computer was then on the network. Even when I first started being around the university in the mid-90s, there were still drop cables coming out the ceilings in places and it being used to connect things. The other thing you needed to make sure is if a signal is travelling down a cable and it comes to an abrupt end, you would get a reflection back along the same cable, which of course would interfere with the data.
Even if it's not attached to anything?
Even if it's not attached to anything. So if you just had it like that, you'd get a reflection back because the signals come to an end and it just sort of reflects back. So that would sort of absorb the energy and terminate the connection. Standard coax cable, RJ8 was a specification for 10^5. I'm not sure what they use in Xerox, but similar sort of stuff, no doubt. Let's have a look at how they actually solve this problem. As soon as you've got some sort of shared medium that machines are communicating over, you need some sort of algorithm, for want of a better word, to decide who can speak when. If you've got a sort of centralized network, which is another way you can build it, a sort of star network as it's referred to, where everything's connected back to a central point, that can arbitrate and only transmit data or receive data from one or send a signal down. It's your turn to send anything. You could do things like that. If you've got a ring network, then you can pass things around as it goes from one machine to another, a token that goes around, a bit like you do on an old single track railway. So only allow one engine train to be on that bit of the line at a time. You have a token that is collected by the train as it goes past and then deposited at the other end to make sure there's only one thing at a time. With Ethernet, with the approach they've taken there, they had a distributed algorithm. So there's no central point except the cable. They've got a distributed algorithm that the machines use based on some principles that are neatly outlined in Bob's memo to decide whether a machine can transmit. And these are sort of based on what was done at Aloha because that had been publicized, it was shown to be working. But they modified it because they were based on a cable. The way Aloha worked, if you go back to the video, is that it transmitted and received on different radio frequencies. So a machine couldn't receive transmissions from other machines because they're on a completely different frequency from what it was receiving on. So if it transmitted at the same time as another machine was transmitting, it had no idea about it. One of the advantages of everything being on the same cable, you can see if something else is being transmitted, which we'll come to. So let's bring up the paper, the memo again, and we get a couple of bits down. There's a whole section on how does a station's transmitter acquire the use of the ether for a particular transmission. But they base it around 4 or 5 axioms, 4 or 5 ideas that they're going to use to make this work. The first one is the ether axiom, as he calls it, and that is that the ether, the cable, carries transmissions to all stations. So if a machine sends a packet of data, it will be received by all stations. It's not being sent specifically to C. If A transmits something, it's sent to everything, and then there's address fields within that which says which machine it's for. And they're transmitted first, because that way all the other machines can ignore it if they're not interested in it. Second one, the proximity axiom, is that the propagation time, basically how far apart the machines are, is relatively small. So if A is sending something to D, it's not going to take too long for it to get there. And by not too long, millionths, billionths of a second, we're talking about. It's all relative when you get down to these things. A long time is a thousandth of a second, which to a human is quite a short time, but it's all relative. The next axiom is the detection axiom. And that states that stations can detect, that's the machines on the network, at all times, transmissions of other stations. So it's not just that they receive it, but they can detect whether something else is transmitting as they pass in about 1 bit's time. So as soon as 1 bit of data from another machine has been transmitted, all the other machines on the network should know that that data is being transmitted and that something is transmitting on the network. So the fourth axiom is referred to as the deference axiom, and this is where we get to the core of how the algorithm works, and we can start to see what's going on. So it says, while detecting a passing transmission, so it's tied into the detection axiom, no other station will begin or continue its own transmission. And this is really the core, the heart of how this system works. It later became known as carrier sense multiple access with collision detection. So let's have a think about how it works. So the basic property is that any machine can send any message and it's received by all the machines, and there's address fields in there that are used to specify who it's going to, and it's down to those machines to say, oh, this is not for me, I'll ignore it. Of course, you can put it into what's known as promiscuous mode and see all the traffic that's traveling past on a network like this. So we can get data from any machine to any other, but the problem we've got, if there's more than one machine wanting to transmit, how do we decide who transmits? If there's only one machine wanting to transmit, then it's fine. It just transmits its data, it gets sent out over the ether, and it's received by all the machines, including hopefully the one that wants to receive it. But if there's two machines wanting to transmit, then we need some way of arbitrating which one gets access. So the first thing is the carrier sense, the deference axiom, and it basically says, if something else is transmitting, don't start transmitting or don't continue your own transmission. So basically we're saying, if you see something else is speaking on the network, if you see something else is transmitting, don't start transmitting. And that will remove a whole load of what we call collisions, where two things are trying to talk at the same time. It's a bit like having a conversation. You wait until the other person is finished speaking.
And then say something.
Exactly. Yeah, because that way it doesn't overlap. Everyone can hear what's saying. So we can get rid of a whole lot of the problems there. But it doesn't get rid of all of them. Let's say we've got machine A transmitting something, and machine B and C both want to transmit a packet. Okay, so we've got machine A transmitting. A's transmitting, so these defer to it and don't send anything. A then stops transmitting. Machines B and C then say, okay, the network's clear, I'm going to transmit. Boom, two machines start transmitting at the same time, so we get a collision. So how do we get around that? Well, the key, as we said, is that these machines can detect if there is a transmission error, if there is a collision, as we call it. And the way that they can do that is that they know what they're sending, but because they're also receiving from the same network, they can compare what they're sending with what's being received. And if they're the same, everything's fine. If they're not the same, then there is a problem. So what do you do if you detect that there's been a collision? And actually you can know, based on the size of the network and the conditions that are there, you can measure that. You can know that within a certain amount of time that you've acquired the network, and the data should, barring accidents, get transmitted without any problem. Because once you've sent enough data that the amount of time it would take to propagate around the whole network and then come back to you has passed, you know that you've got the bus acquired and you can send everything, because all the machines, if they follow the algorithm correctly, will have detected that you're transmitting and not send anything. You can get a situation where if you start sending and machine D is several hundred meters away, that by the time it starts transmitting when it's clear, you've already started transmitting. And if that happens right at the end of that time period it takes to get there, it'll take the same time to get back, and so it can be potentially twice the distance to propagate the full length of the network. So we can get collisions, we can detect them, so we can then stop transmitting and stop the collision. The next thing that comes up is, well, how do we then send the data. And the way that they do this is they actually use what's called exponential backoff, has been termed that afterwards. And basically, these two machines, B and C, were trying to transmit, and they've detected that a collision has happened. How do you decide next?
Well, they're not talking to each other because the network is the conversation, is the communication media. So presumably they've got to kind of pick a random amount of time or something like this, right?
Exactly right. So what you do is you say, okay, machines B and C both want to transmit, they've detected a collision, they say, right, I'm going to...
roll the dice or something.
Yeah, they'll pick a random number, and they will wait that long, in seconds, but they're clever. They know, well, they think, actually, it's going to be twice the length of the network in time that I need. I'll pick a number between that distance at random. So I pick a random number, and there's various ways you can do that, and I will wait that long and then try transmitting again. If something else starts transmitting before then, well, I defer and the whole thing starts again because something's got in before me. Otherwise, I will pick a number and wait that time. And hopefully, if they pick random numbers, they'll be different. So one of them will start transmitting, and the data will get through, and then the other one will say, oh, something else is using the network. You can get to the point, though, where if the network gets busy, then you've got lots of machines on it, and they're all trying to transmit, that your probability of a collision happening, even though you've had a collision and they're picking random times, become so high. The more machines on the network that are trying to transmit, the chances that they'll pick the same duration or very similar durations becomes more likely than not. Well, then what do? Well, you get another collision. What those machines then do is they do the same thing again. Oh, we had another collision. Just after having a collision, we'll pick a random number. But this time, they double the maximum wait time. So if they waited for it to go twice around the network before, they'll now wait for it to go 4 times around the network. And if it still collides, well, you double it again, and you go on until eventually the data gets through. And so by using all those different aspects, they can get it to the point where, without any of the machines being able to need to talk to each other directly, they can acquire access to the ether to send the data when they need to. Now, that doesn't guarantee the data is going to be received correctly. I mean, the machine needs to be switched on. There might still be noise. Someone might switch a vacuum cleaner on right next to the cable, which would introduce some temporary noise on the system or something. There might be a dodgy cable connection somewhere, which would then corrupt the packet, and so you still have to have error checking there. And if the machine's switched off, you're not going to know it hasn't been received unless something sends thing back. But it can do its best effort. It's just what's referred to as a best effort network at getting the data transmitted. And that was how the original Ethernet worked. I mean, originally it ran at 3 megabits. It was designed to connect the Xerox Alto workstations, PDP-11s, PDP others, Novas together at Xerox PARC. But it became incredibly popular. It sort of escaped. Other companies started implementing it. And it quickly, certainly through the 80s and the 90s, I mean, it wasn't the only networking standards. There were others about, Token Ring, Econet, what else? We had ArcNet were around, but it was very much Ethernet that won out, probably because it wasn't the cheaper option, but it just became the standard that people use, and the others sort of fell by the wayside, probably because it was easiest to implement or something. I don't know why it became popular, but it did. And these days, pretty much all networking connections that we use are based in some form off the original Ethernet. Now, these days, they don't use a shared medium. There's not masses of Ethernet cable running around this building with all the machines attached onto it. One of the big problems with a shared medium network like Wi-Fi is the more machines you have on there, the less bandwidth there is around. We talked about this in another video. The less bandwidth there is around for each machine to communicate. So particularly on wired networks, you'll get them to be switch-based now. But actually, all that does is say, well, okay, we're going to have a central point, and between the machine and the switch, we'll run Ethernet, but there's only one machine on there, so there's not going to be any collisions, but we'll send the data in the same way or with the same packet format and different modulations, so the speeds increase from 3 megabit to 10 megabit to 100 megabit to gigabit to 10 gigabit, then down to 2.5 and 5 gigabit, 25 gigabit, 40 gigabit, 100 gigabit, 400 gigabit, wherever we've got to in terms of networking. The speeds changed, the mediums changed from RJ8 to 10^2 to UTP, Cat5, Cat6, Cat7, fiber optics, whatever you're using it. And with the switch, what happens is that you send the packet to the switch, and the switch will look at it and say, oh, this is for this machine, and I know that this machine is on this network here, on this port here, so I'll queue it to go out there at that point, and you can get full duplex communication. But this is where it began 50 years ago at the time of recording, designed around this. And yeah, it's quite a nifty algorithm to solve those problems. It's not the only one. There's other approaches that people have used. We talked about Wi-Fi in another video, and that use carrier sense and multiple access, but with collision avoidance, because as we talked about the hidden node problem, you can't always, when you're on a radio-based network, detect because something might be out of range of where you are, but there are other approaches that you can use to sort of share access to this shared medium. If you're wondering why we've got red and blue ends of the room, well, this is because we use this for cybersecurity, amongst other things, when we're teaching, and so we can do red team, blue team. The actual lights are for another purpose, which is probably a video in its own. They react to the state of the room, and I shall leave it at that.